In this video we're going to look at a practical way of finding the constants from a partial fraction expansion. Now this method is called the cover-up rule. Now rather than describing it in words, it's best just to go through a couple of examples. So let's look at this example first of all. The inverse Laplace transform of 5s minus a upon s times s minus 4. Well, we've seen from partial fraction expansion that this could be written as a upon s plus b upon s minus 4. Now in the cover-up rule, we take the first term here, a upon s, we cover up the s here in this equation, and then we see what's left over. So what's left over is 5s minus a upon s minus 4. So I've written that down here, 5s minus a upon s minus 4. And then we take the limit as this value s here tends towards 0. So that's the limit as s tends towards 0 of 5s minus a upon s minus 4, which equals minus a upon minus 4, which equals 2. So the value for a equals 2. Now let's look at the second one, b upon s minus 4. We cover up the s minus 4 and we're left with 5s minus a upon s. So I wrote that down here, 5s minus a upon s. Now we take the limit as the root tends towards 0. So that is s minus 4 equals 0 or s equals 4. So it's the limit as s tends to 4 of 5s minus a upon s, which equals 20 minus a upon 4, which equals 12 upon 4, which equals 3, so b equals 3. So putting a and b into the equation above, we've got the inverse Laplace transform of 2 upon s plus 3 upon s minus 4, which equals 2 plus 3e to the 4t. Let's look at our second example. We're looking for the inverse Laplace transform of 2s squared minus 4 upon s minus 3 s minus 2s plus 1. So we've seen from partial fraction expansion that can be written as a upon s minus 3 plus b upon s minus 2 plus c upon s plus 1. Now using the cover up rule for the a term, if we cover up the s minus 3, we're left with the 2s squared minus 4 upon s minus 2 s plus 1. And then what we do is we take the limit as the root tends towards 0. So s minus 3 equals 0, that is s minus s equals 3. So it's the limit as s tends towards 3 of this here, which gives us a value of 7 upon 2, which is then a. Similarly, we do the same thing for b. We cover up the s minus 2, and on the denominator we're left with the s minus 3s plus 1. And then we take the limit as s tends towards 2, which gives us a value of minus 4 upon 3 for b. Similarly for c, we cover up the s plus 1 and we're left with the s minus 3 s minus 2, and we take the limit as s tends towards minus 1. So that gives us minus 2 upon 12, which equals minus 1 upon 6. So therefore we can put the a, b and c values in and we get 7 upon 2 all upon s minus 3, minus 4 upon 3 all upon s minus 2, minus 1 upon 16 all upon s plus 1. So the inverse Laplace transform of that is 7 upon 2 e to the 3t, minus 4 upon 3 e to the 2t, minus 1 upon 6 e to the minus t. So you can see that this method is very quick and very efficient, very effective, and this is the method that we'll tend to use invariably when you're trying to work out these values for the constants for partial fraction expansions. So thank you for listening and goodbye.